This is your presenter, Asloob Mudassar, and I am presenting slide number 14A of the course on atomic and molecular physics. This is a series of at least 2 or 3 lectures in which atoms are subjected to external electric field. In the 2 days lecture, I shall be covering the following topics: atoms in an electric field, Stark effect. Two main types of Stark effects will be discussed, that is the linear and quadratic Stark effects, and the splitting of H alpha, H beta, and H gamma lines of the hydrogen atom under linear Stark effect. So these topics will be covered in the 2 days lecture. Atoms in an electric field. Stark effect reported in the year 1913. Stark observed splitting of lines of the Balmer series as emission spectrum of hydrogen atom contained in the electric field of a condenser. That is, here we are applying electric field to the atoms of a hydrogen atom. This was reported in the year 1913. Frequency shift in optical spectra in the presence of electric field is called Stark effect. So what is the Stark effect? That is, the frequency shifts occur in the optical spectra when the atoms are subjected to external electric field. So the electric field will be abbreviated as EF and the Stark effects will be abbreviated as SE. So if there is a linear Stark effect, it will be abbreviated as LSE. And if I am talking about a quadratic Stark effect, it will be represented or abbreviated as QSE. So SE, that is the Stark effect, is more difficult to observe than the Zeeman effect because the strong electric fields without sparking is required. So in case of Stark effect, we need the application of strong electric fields, and at the same time we require that the electric fields do not spark. So under very careful conditions, we apply a strong electric field to the atoms, and moreover, this phenomena, that is the Stark effect, is difficult to observe as compared with the Zeeman effect. Stark effect is far less important than the Zeeman effect. So Zeeman effect has got more applications in comparison with the Stark effect as far as the atomic physics is concerned. But here we shall see that also there are some definite applications related to the Stark effect. So splitting of terms from hydrogen-like atoms. So you see that here I am talking about hydrogen-like atoms. That is the atom which have single valence electron. So splitting of terms from hydrogen-like atoms for all electrons except the s electron, for which L is equal to 0 under the applied electric field E is proportional to E, called linear Stark effect. So you see that here I am talking about number one thing is the hydrogen-like atoms. And the hydrogen-like atoms in this case will be helium singly ionized, lithium doubly ionized, beryllium triply ionized. These atoms are hydrogen-like atoms because they contain only one single valence electron outside the nucleus. So here I am talking about these hydrogen-like atoms, and I am talking about those atoms in this category which do not have the s electrons. That is, I am not talking about the s electrons for which the orbital quantum number is 0. I am talking about, for example, the p electron, the d electron, or the f electron. So that's why I am applying electric field to the hydrogen-like atoms, but the electron should not be an s electron. It could be a p electron, it could be a d electron, or it could be an f electron. So let me read again. Splitting of terms from hydrogen-like atoms for all electrons except the s electron, for which the orbital quantum number is 0. So excluding the s electron, we are applying electric field which is capital E, and we found that the splitting is proportional to the electric field E, which we call as the linear Stark effect. because in the linear star effect, the splitting is directly proportional to the first power of electric field. That is why it is called the linear star effect. And here simply I am writing that for the hydrogen like atom, and for those electrons for which the orbital quantum number is not zero, that is, I am talking about p electron or d electron or f electron, then delta E, which is the splitting between the levels, is directly proportional to the electric field, or is directly proportional to the first power of the electric field. That is why equation 14(1) represents symbolically the linear star effect for the hydrogen-like atoms. And the hydrogen-like atoms are what I have discussed: helium singly ionized, lithium doubly ionized, beryllium triply ionized are examples of the hydrogen-like atoms. In a linear Stark effect, the L degeneracy is lifted if it is not lifted already by internal atomic fields. So lifting of orbital, you know that in hydrogen atom and in hydrogen-like atom, it is the principal quantum number which mainly determines the energy of levels, especially in case of hydrogen atoms. We have n is equal to 1 level, n is equal to 2 level, n is equal to 3 levels. And here we designate that the energy with a symbol n, that is En. That is, the energy is principally or mainly determined by the principal quantum number n. But you know that when we apply the electric field, the energy becomes dependent besides the principal quantum number n on the orbital quantum number L. So we say that the L degeneracy is lifted. That is, before that, L degeneracy is lifted mean that the energy is now depending upon another quantum number, which is the orbital quantum number. So in the linear Stark effect, that is when we apply the electric field, and in the cases when the splitting of energy states is directly proportional to the linear power of the electric field, as shown in equation number 14.1, the L degeneracy is lifted. That is the energy of the levels is now depending on two quantum numbers, that is the principal quantum number n and on the orbital quantum number L. It is not lifted already. That is, in some atoms, if the L degeneracy is not lifted, then by applying the electric field, the L degeneracy is lifted. And you know that in some atoms, for example, in alkali metal atoms, the L degeneracy is lifted by the internal composition of the atom. And when we apply the electric field, then of course the two will also determine the same thing, that is the internal structure of the atom lift the orbital degeneracy, for example, as in the case of alkali metal atoms. And when we apply the electric field, external electric field, then of course this will also superimpose the previous lifting of L degeneracy, which we shall see. Now, the energy of an atom, which depends on the principal quantum number n, for the hydrogen-like atoms will now depend upon the orbital quantum number L as well. That's why I have labeled the energy by the two quantum numbers n and L. And this is possible when n and L does not exist already. So if the orbital degeneracy is not present already, then of course the orbital degeneracy is lifted under the application of the electric field, of the external electric field. That is, the energy which was only depending upon the principal quantum number n is now going to depend on the principal quantum number n as well as on the orbital quantum number L. And this dependence on the orbital quantum number L is mean that the L degeneracy is lifted with the application of the applied electric field. Displacement and splitting. So you see that these are the two things. One is the displacement, that the levels are displaced, and the second thing is that the splitting between the level is changed. So the displacement and splitting of terms in non-hydrogenic atoms is proportional to E square, called quadratic Stark effect. So you see that in some atoms which we regard them as non-hydrogenic atoms, for such atoms, when we apply the electric field, the displacement and the splitting in such atoms will be proportional to E square, that is to the square of applied electric field. Such an effect is referred to as the quadratic Stark effect, represented or abbreviated as QSE. And simply we can write that the atoms which are non-hydrogenic, for such atoms the splitting between the energy levels delta E is proportional to the quadratic power, or power of is proportional to the square of the electric field, as shown in equation number 2. Among other atoms, for example, alkali metal atoms are also non-hydrogenic atoms because the inner core contains many number of electrons there. Though the valence electron in alkali metal atoms resembles that of the hydrogen atom, but you know that besides that there are electrons there are atoms around the nucleus in closed orbits. Understanding quadratic Stark effect qualitatively using intuitive model. So you see that here I am going to represent the quadratic Stark effect, but just intuitively and not using strict mathematical equations. Applied electric field induces electric dipole moment P in an atom. That is P, that is the electric dipole moment in an atom, is proportional to the electric field, or in the form of equation we can write that the electric dipole moment P in an atom is equal to alpha times the applied electric field E, as shown in equation number 3. Alpha is the atomic polarizability, or alpha may be referred to as alpha quantum number of an atomic state. So you see that in this case we can also refer alpha as the quantum number, but in principle alpha is actually the atomic polarizability. Alpha changes with the change of quantum state of an atom. For example, if the atom is in a different quantum state, then of course the value of alpha will be different. So alpha changes with the change in quantum state of an atom, or equivalently with the change of electronic configuration. So when the electronic configuration is changed in an atom, that is the quantum state of an atom is changed, then the electron distribution is also changed, and due to that one, the alpha, which is the atomic polarizability of that atom, in condition in proportional with that particular atomic state, will also change. So alpha will also change with regard to a particular atomic state in an atom. The interaction of the applied electric field with the induced electric dipole moment in an atom gives rise to interaction energy given by. So you see that when we apply electric field and external electric field E to the atom, what will happen? There is an induced electric dipole moment P, and there will also be an interaction with the electric dipole moment P and the electric field. And so the interaction energy is stored in an atom, which is given by equation number 4. That is capital V. The interaction energy in an atom is equal to half times the dot product between the P and E. So if you substitute the value of P from equation number 3, you will get this equation to be equal to half into alpha times E dot E will be equal to half times alpha E square. And you know that here the interaction energy V is now going to depend upon the quadratic value of E, that is to the square value of applied electric field. So such an effect in which the interaction energy depends directly on the square of the electric field is referred to as the quadratic Stark effect. And here we can write from equation number 4 that V is directly proportional to e to the power 2. This is the qualitative demonstration of quadratic Stark effect, which is now going to be presented. So up to equation number 15, sorry, up to equation number 5, we have demonstrated the inductive way of quadratic Stark effect. Now I am going to present the qualitative demonstration of a quadratic Stark effect. Splitting of terms in a magnetic field, which we call as the Zeeman effect, depends on the magnetic quantum number mj, which takes the value from j to minus j in terms of integer difference. That is j, then j minus 1, then j minus 2, and so on up to minus j. That is, there is a splitting of a term into two j plus 1 values. So you see that when we have seen in the previous slides that when we apply the magnetic field to an atom, which we refer to as the Zeeman effect, then of course the total quantum number J of the atom is now lifted. The J degeneracy of the atom is lifted, and the energy of the atom is now will now depend upon the magnetic quantum number mj, which ranges from 0 to plus minus 1, plus minus 2, up to so on up to plus minus j. That is, there will be 2j plus 1 values of mj. That is, the j degeneracy is lifted into 2j plus 1 sub levels. This is what we have seen in case of Zeeman effect. But you know that in case of Stark effect, the the splitting will depend not upon the value of mj as in case of Zeeman effect, but on the magnitude of mj values. That is, the positive mj value and negative mj value having the same magnitude will represent a single sublevel. So in linear Stark effect, splitting of terms depend on the mod of mj. And also in the quadratic Stark effect, the value of splitting of the levels will depend upon the mod of mj levels, which takes values from mod of plus minus mj, plus minus j, plus minus j, plus minus j minus 1, and so on up to 0. Or in other way, you can say that is the mod of 0, plus minus 1, plus minus 2, and so on up to plus minus j. That is, will split into j plus 1 values for j being an integer, or into j plus half values for j being a half integer. So this is the case of Stark effect, both for the also applicable to the quadratic Stark effect, that in the quadratic Stark effect, the splitting of the levels will depend upon the mod of mj levels. So mj levels may be considered here as the magnetic quantum number, which is also proportional to the same quantum number we have used in the Zeeman effect, or you can may label as the electric magnetic as the electric quantum number mg. And you know that its values are equal to j plus 1, not 2j plus 1 as in case of Zeeman effect. And when it is an integer, and when j is a half integer, then the values of mj mod will be equal to j plus half. In mj mod, or in the mod of mj, the total magnetic quantum number mj, or you may refer it as the electric quantum number mj, as in case of applied magnetic field ze, is also considered to split the levels in case of applied electric field se. So you see that in Zeeman effect, the levels are splitted by the magnetic quantum number mj. But you know that in case of electric field, the splitting of these levels will depend upon the mod of mj values, and this mod of mj values will be determined by the electric field and not by the magnetic field. So in the Stark effect, the splitting is determined by the mod of mj values, and these mj values may be referred to as the electric quantum number of the atom. So if mj mod is the same for two states of an atom, then the splitting for such states will also be identical. Because you see that if we have mj value as plus minus 3, then the mod of plus minus 3 will be 3. So it means that both plus 3 level and minus 3 level will be represented by a single level in the Stark effect. The total effect of the electric field on a clockwise or on a counterclockwise rotating electron when averaged over time would be the same provided the electrons have identical spatial distributions. So if we are considering the electrons having identical spatial distributions, whether they are revolving clockwise or anti-clockwise, then you see that the electric field will have the same effect on them. So the effect of electric field on a clockwise or on a counterclockwise rotating electron when average over time would be the same. That is, the effect of electric field would be the same provided the electrons have identical spatial distribution. Shift in the Stark effect increases with principal quantum number n. So if we are talking about an atom in a state having a higher quantum, having higher principal quantum number n, then of course the shift in the Stark effect will also be greater. That is, the splitting or the shift in the Stark effect will be proportional to the value of n. The greater the value of n, the greater would be the shift in the levels in the Stark effect. Orbits with larger n have larger polarizability alpha. So the greater the size of an atom, the greater will be the polarizability of the atom. That is, the greater will be the value of alpha. On this basis, the Stark effect is extremely important for the investigation of Rydberg atoms. You know that Rydberg atoms are considered to be the largest atoms. And for these larger sized atoms, the polarizability of the atoms will be much greater under the application of the electric field. So we can easily discriminate between different Rydberg states of an atom, also depending upon the value of polarizability or on the shift in the electric fields or in the shift in the Stark effects under the application of the applied electric field. Due to chemical bonding between atoms in a molecule, strong electric fields are induced producing Stark effect. So you see that here I am not talking about the applied electric field, but I am talking about the electric field which is resulted by the chemical bonding between the atoms. So due to chemical bonding between atoms in a molecule, strong electric fields are induced producing the Stark effect. This induced Stark effect is helpful in the understanding of molecular spectra. So here I am not talking about the molecular spectra under the application, under the production or under the induced electric field produced within the atom, produced within a molecule. I am not talking about the molecular spectra now, but I am constraining myself to the atomic spectra under the application of the applied electric field. So you see that here I am going to discuss the quadratic Stark effect for the sodium D lines. So there are two sodium D lines, D1 line and D2 line. And for the sodium atom, we have seen that the ground state is 2s half, and the first two excited state are 2p1 half and 2p3 half. And this is under the application, and this is under the case when there is no electric field. And you know that the green line, the green transition will represent the sodium D1 line, and the red line will represent the sodium D2 line. And these two lines are allowed under the optical transition that delta L is equal to plus minus 1. That is, the change in the orbital quantum number should be equal to plus minus 1 for these transitions to occur. So the transition from P1 half to S1 half, and then the transition from P3 half to S1 half. These will give you respectively D1 lines, sodium D1 lines and sodium D2 lines represented in green and red under the case then when electric field is approximately equal to 0 or when there is no electric field. Now what we are going to do is that we are going to apply the same atom, that is the sodium atom, with an electric field of the order of 10 to the power 5 volt per centimeter. And there we shall observe the shifting of or the displacement of the levels. You can see that the dotted level represents the reference level in an atom under when there is no electric field, and you see that these solid lines are shifted downward under the application of the electric field. So when the electric field of the order of 10 to the power volt, 10 to the power 5 volt per centimeter is applied, the levels are shifted downward with respect to the reference level shown in a dotted line. And these two levels can be inferred from the value of J, which is 3 by 2. So for this J value 3 by 2, the J degeneracy will be lifted, and then we have Mj values. But you know that in the case of electric field, we have the Mj mod values. So for these two levels, the Mj mod values will be equal to plus minus 3 by 2 mod and mod of plus minus half. You know that when the value of J is 3 by 2, then the allowed values of Mj will be equal to plus minus 3 by 2 and plus minus half. And you know that in the Stark effect, we have to take the absolute value of these Mj values. So the Mj, we have taken the absolute value of a plus minus 3 by 2, and again we have taken the absolute value of a plus minus half. These are the allowed values of Mj, and these can inferred from the total value of J, which is 3 by 2. And you know that these two levels have shifted downward under the application of the applied electric field. Now consider the level P1 half. Under the same applied electric field, which is of the order of 10 to the power 5 volt per centimeter, the value of J, which is equal to 1 half, is split into Mj values, which is actually the mod of Mj values equal to plus minus of half. And you know that this shifting is much larger in comparison with the shifting of the other levels shown corresponding to P3 half levels. Then you see that we are now going to consider the ground state. When under the same application of the electric field, the ground state is also shifted. But you know that this shift is smaller. In comparison, you see that the reference line for the ground state is also shown in the dotted line, horizontal dotted line, and the level is shifted downward. Now the value of J, quantum number J, is half for the 2s half state. And this J is equal to half value will be split into Mj mod value, which is Mj is equal to plus minus half. So I have shown these values in the form of mod of Mj values. Two values corresponding to state P3 half, one level corresponding to P1 half, and one level corresponding to S1 half. So you see that now I have shown the transition between these levels. The transition with the original levels in the absence of the electric field is shown by the dotted line. For example, the longest dotted line also corresponds to this red line under the application under no electric field. And the second dotted line, that is this one, corresponds to the line in green under no electric field. So these actually dotted lines provide you the reference D1 line and D2 line. Now you see that I have shown three transitions between the levels allowed by the Mj, because the levels which will be allowed will follow the selection rule that delta Mj could be equal to 0 and plus minus 1. In principle, you should say delta Mj mod should be equal to 0 plus minus 1. Under that optical selection rule, three transitions are shown. One is in green, one is in red. The other one is in red, which follows delta Mj is equal to plus 1. The other is in green, which follows delta Mj is equal to 0. The third one is in blue, which follows delta Mj is equal to minus 1. So these three transitions have been shown. And you know that this quadratic Stark effect for the sodium D lines is also triplet. That is three lines are obtained. And these three lines have different frequencies. So this is the main difference of the quadratic triplet of the quadratic Stark effect or the quadratic triplet from the Zeeman triplet. In the Zeeman triplet, the three lines are obtained, but you know that those three lines may have the same frequency. But you know that in case of the quadratic Stark effect, you will see that these are the triplet lines, but these triplet lines have different frequencies. So here you see that in this figure, I have demonstrated the quadratic Stark effect of the for the sodium D lines under the application of the electric field, which has a magnitude of 10 to the power 5 volt per centimeter, and the quantum states are determined by the value of mj mod, and J value is obtained as for example 3 by 2 from the 2p3 state, and J is equal to half from the value of 2p half state, and similarly J is equal to half from the value of 2s half state. So these J values will split into mj values in order to determine these states corresponding to the Stark effect, and the transitions have also been shown. And here you will notice that there is a shift in frequencies under the Stark effect, and the shift has been shown only for the red lines in comparison with the dotted lines, which is equal to 0.05 angstrom. So when we apply an electric field of the order of 10 to the power 5 volt per centimeter, then of course the frequency shift that will be produced by this electric field for the sodium D2 lines will be equal to 0.05 angstrom. The energy shift delta E for the sodium under the applied electric field leads to quadratic Stark effect. That is, delta E is equal to minus half times alpha times E square, where alpha is the polarizability which differs from state to state. That is, from 2p3 half and 2p1 half. These two states have different polarizabilities, that is, different values of alpha, and thus undergo different shifts. So if you put the different values of alpha for these states, then of course the value of delta E, that is the change in shift in the energy of these levels, will be different. These levels shift, these level shifts based on the values of mj mod, where mj times h bar is the projection of the total angular momentum j in the direction of the applied electric field. And you know that mj mod, as in case of Zeeman effect, we have learned that mj is actually the quantum number, which is actually the projection as in the form of mjh bar of the total quantum number j in the direction of the magnetic field. Similarly, mj mod is actually the projection of mjh bar in the direction of the electric field of the total angular momentum j of the atom. So mjh bar is actually the projection of the angular momentum j of the atom in the direction of the electric field. But here we consider only its magnitude, which is mj mod. The ground state, which is 3 2s half, has j is equal to half, and thus mj is equal to half, does not split. So the level does not split but shifts downward. So you see that in the diagram, you can see that the level corresponding to the ground state is shifted downward, but that remains a single level. So the level is not splitted, but the level is shifted. Similarly, for the first upper level, which is a 2p half level, has j is equal to half, and mj mod is equal to half, does not split but shifts downward. So here in the figure you can see that the first excited level, which is p1 half level, is shifted downward, but it is not split into more levels. So the level is again a single level, but shifts downward. Then for the second excited state, which is the 2p3 half, has j value is equal to 3 half, and thus mj mod values will be equal to 3 half and 1 half. So this level 2p 3 half level will split into two levels due to two different polarizabilities and both shift downward also. So here for the second excited state, which is a p 3 half state, you can see that this state is split into two levels. And the second thing that you will notice also is that these levels are also shifted in energy downward. In D1 line, that is transition from P1 half to S1 half, both the upper and the lower levels have only one value, which is mod of mg is equal to half, gives a single transition shifted frequency, that is no multiple splitting is obtained. So in the D2 line, that is the splitting from P, that is from the state transition from the state P 3 half to the state S half. Both upper and lower levels have 2 and 1 values of mod mj, and the upper level splits into two levels, and thus D2 line splits into two distinct frequency components. Since in this transition P3 half level has two levels and PS and S half level is a single level under the application of electric field. So the transition from the two upper levels corresponding to P3 half to the one level in the ground state will give you two distinct frequencies, two components of the frequencies corresponding to the D2 lines. And you can see those two lines as represented by the red line and by the green line in these two transitions. The splitting in sodium is not symmetric, and the levels shift downward in comparison with the levels in the absence of electric field due to quantum defect associated with sodium atom. You see that I have discussed the quantum defect when I discussed the alkali metal atoms. So you can go through those lectures related to alkali metal atoms. So due to quantum defect associated with the sodium atom, the states in the sodium are already shifted by large energy gaps. There is a small shift in these gaps due to the quadratic Stark effect. So that the splitting of these sodium levels is already there due to the quantum defect, which is due to the resultant, which is due to the effect of the electrons in the cloud orbits around the nucleus. But you know that there is also a small shift in these gaps due to the quadratic Stark effect. The components of D2 lines corresponding to delta Mj is equal to 0 has a pi polarization, where the second component corresponding to delta Mj is equal to 1 has a sigma polarization. The pi polarization means that the electric field of the light is parallel to the direction of the applied electric field. And the value and the sigma polarization mean that the light which is emitted is also polarized, but it has an electric field which is perpendicular to the direction of the applied electric field. That is, the electric field of the light is perpendicular to the applied electric field. Sodium and other alkali metal atoms exhibit quadratic Stark effect. The valence electrons in these atoms experience non-Coulombic potential due to the presence of the inner electrons in closed shells, and due to this L degeneracy, that is the level corresponding to principal quantum number 3 will be shifted and will be split as 3s, and 3p for the sodium is shifted even when electric field is 0. So even under the effect of no electric field, the L degeneracy for the sodium, for the alkali metal atoms is lifted. That is, the case of sodium is presented as the splitting into 3s and 3p levels for the sodium represents splitting into two levels, and this splitting lifts the L degeneracy, that is the level is splitted, that is the level with the principal quantum number n is equal to 3 is split into two levels, that is 3s level and 3p levels, even when there is no electric field. But if you apply the electric field, that is then these levels are further shifted downward in energy. Now I am going to discuss in greater detail the splitting of H alpha, H beta and H gamma lines under the linear Stark effect. So you see that when we are going to study the hydrogen atom, we shall consider that the hydrogen atoms in the hydrogen atoms under the application of the electric field, we only observe the linear Stark effect. So what will be the splitting of H alpha, H beta and H gamma lines under linear Stark effect? So the splitting of H alpha, H beta and H gamma lines will be represented in the next slide. So this is the end of slide number 14A of the course on atomic and molecular physics. The lecture is continued. That is the lecture under the title of atoms under the application of applied electric field is continued, and 2 to 3 lectures will be presented further in this collection.